Now we have seen that some functions have extreme values, whereas others do not. The following theorem gives conditions under which a function is guaranteed to possess extreme values. In definition number 3, the extreme value theorem. If f is continuous on a closed interval a to b, then the function f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the closed interval from a to b. The extreme value theorem you can see is illustrated below. Note that an extreme value can take on more than once. Although the extreme value theorem is intuitively very plausible, it is difficult to prove, and so we omit the proof. So here we can see that between the interval of a and b, we can see that we have an absolute maximum at f of c, or c f of c. So this is going to be considered the maximum, or the absolute maximum. And the point f of d, df of d, is going to be the absolute minimum. Okay, same thing here. We can see that this represents the absolute max, where this endpoint represents the absolute minimum. Okay, and then here we can see that both C1 and C2 are both absolute maximums. And we can see that D is considered the absolute minimum. Okay. Now, let's continue here. Now, figures here below show that a function need not possess extreme values if either hypothesis, continuity, or closed interval is omitted from the extreme value theorem. So we can see here that this function has a minimum value at f of 2, which is equal to 0. So therefore, this is an endpoint. Okay, that endpoint is telling us that it has a minimum value. Okay, but it does not have a maximum value, because you can see here when it gets to this point, then it gets closer to 3, but it doesn't have an endpoint there. So therefore, this is considered the minimum value. Okay, over here, this continuous function g has no maximum or minimum, because we have an undefined point here, and therefore this is going towards a vertical asymptote. So again, the function f, whose graph is shown in the figure on the left here, is defined on the closed interval from 0 to 2, but has no maximum value. Now notice that the range of f goes from 0 to 3. The function takes on values arbitrarily close to 3, but never actually attains the value of 3. This does not contradict the extreme value theorem because f is not continuous. Nonetheless, a discontinuous function could have maximum and minimum values. Now the function g over here on the right, shown in this figure, is continuous on the open interval from 0 to 2, but has neither a maximum nor a minimum value. Now the range of g goes from 1 to positive infinity, so the function takes on arbitrarily large values. Now this does not contradict the extreme value theorem because the open interval from 0 to 2 is not closed. Now the extreme value theorem says that a continuous function on a closed interval has a maximum value and a maximum value and a minimum value. But it does not tell us how to find these extreme values. We start by looking for local extreme values. Now in the figure below here, it shows the graph of a function f with a local maximum at c and a local minimum at d. So it appears that at the maximum and minimum points, the tangent lines are horizontal, and therefore each has a slope of 0. We know that the derivative is the slope of the tangent line. So it appears that f prime of c is equal to 0, and f prime of d is equal to 0. So the following theorem says that this is always true for differentiable functions. Fermat's theorem. If f is a local maximum or minimum at a value of c, and if f prime of c exists, then we know that f prime of c is equal to 0. Now, although Fermat's theorem is very useful, we have to guard against reading too much into it. Now, if we look at the function f of x is equal to x cubed, then the derivative of that function is 3x squared. So f prime of 0 is equal to 0. But in that function, we know that it didn't have a maximum or a minimum at 0. So you can see from its graph here below that the fact f prime of 0 equals 0 simply means that the curve y equals x cubed has a horizontal tangent at 0, 0. Instead of having a maximum or minimum at 0, 0, the curve crosses its horizontal tangent there. Thus, when f prime of c is equal to 0, f doesn't necessarily have a maximum or minimum at that value of c. So in other words, the converse of Fermat's theorem is false in general. Now we should bear in mind that there may be an extreme value where f of prime of c does not exist. So for instance, the function f of x, which is equal to the absolute value of x, has its local and absolute minimum value at 0, as you can see here below. But the value cannot be found by setting f prime of x equals 0, because as was shown in example 6 in section 2.7, it does not exist because it is a corner. So remember that corners, the value will not exist. Now, Fermat's theorem does suggest that we should at least start looking for extreme values of f at the number c, where f prime of c is equal to 0, or when f prime of c does not exist. Such numbers are given a special name. So for definition number 5, a critical number of a function f is a number c in a domain of f such that f prime of c is equal to 0 or f prime of c does not exist.